Now that we've learned some distributions, we can use them for statistical inference. We use statistics from a sample to infer things about parameters from a population. In a hypothesis test, we specify a hypothesis about some parameter. Then we gather data, compute a statistic, and use it to determine whether our hypothesis was correct. The hypothesis test was invented by this guy named R.A. Fisher, and he's basically the father of modern statistics. Besides the hypothesis test, he invented a bunch of techniques we still use today, but he was also into eugenics, and in the 50s, when people started drawing conclusions about smoking and lung disease, he was ridiculously skeptical of it. So today, he's not held in as high regard as he could be. Anyway, let's look at how this works. The test Fisher invented was a little more complicated than what I'm describing because of how he randomized things and made the decision. I'm going to adjust it a little so that we can use the binomial distribution. I've linked to the Wikipedia page about this story if you want to see the original version. So, it begins with R.A. Fisher at a dinner party, and a woman announces to everyone that she can tell the difference between tea added to milk and milk added to tea. If you give her a cup of tea with milk, she can tell what's been added first. Fisher decided to test her claim. They prepared 8 cups of tea where the order of milk and tea were randomly assigned. So think of it like they flipped a coin to decide which should come first for each cup. Let's assume that the woman is lying and that she can't tell the difference, so she's just guessing. Then what we have is a binomial distribution. Her probability of success is zero point 0.5, and there are 8 trials. It turns out that the woman was correct on all 8 cups. The probability of that happening, according to the binomial distribution, is 1/2 to the 8th, which is 1 out of 256. Because this probability is so low, it makes us think that our assumption that she was lying was wrong, and that she actually can tell the difference. We have this statistical evidence that she's not lying, and that's the idea behind a hypothesis test. You make an assumption, you collect data and compute a statistic, you look at the probability of getting a statistic like that under your assumption. If that probability is really low, you reject your assumption. What if the woman correctly identified 7 of the 8 cups? Should we still conclude that she's just guessing? The probability of getting at least 7 correct by guessing is 0.035, which is low, but it's not that low. It's about 1 in 29. When we perform these tests, we need some kind of decision rule, a cutoff that tells us when to reject our assumption. It all depends on the situation, but traditionally the cutoff is 0.05. If a probability of a result as extreme as what we saw is less than 0.05, we reject our assumption. Formally, this assumption that we make is called the null hypothesis. The notation for it is H0, aka H0. The hypothesis that we're trying to prove is called the alternative hypothesis, and we write that as HA. In the lady tasting tea example, the null hypothesis, H0, was that she was just guessing, or that her probability of getting the order correct was P equals 0.5. The alternative hypothesis was that she could tell the difference, that her probability of identifying the tea was greater than 0.5. We always assume that the null hypothesis is true. Under the null hypothesis, the test statistic will follow some distribution. This allows us to compute the probability of getting the test statistic under the null hypothesis. If this probability is really low, we will reject the null hypothesis and accept the alternative. This probability is referred to as the p-value. The rejection region of the distribution determines how low the p-value has to be in order to reject the null hypothesis. Like I said before, traditionally it's set at 0.05, but it can be whatever you want depending on what you're doing. HA is what you're trying to prove. In general, the null hypothesis is the uninteresting result. The null hypothesis is that nothing's going on, and the alternative is that something is going on. For example, if you think smoking causes lung cancer, your null hypothesis is that smoking doesn't cause lung cancer. It could be that the proportion of smokers who develop lung cancer is the same as the proportion of non-smokers who'd get it. The alternative hypothesis would be that the proportion of smokers who develop cancer is greater than the proportion of non-smokers who get it. Then you would collect data and see what it tells you. Once you've established your hypotheses, you compute a test statistic and compare it to a reference distribution. The reference distribution is the distribution that the statistic would follow if the null were true. We specify a rejection region of our reference distribution. If the statistic lands in that region, then we will reject the null hypothesis. In the lady tasting tea example, the test statistic is the count of correct identifications. The reference distribution is the binomial distribution with n equals 8 and p equals 0.5. The rejection region depends on what we're testing and how confident we want to be. But in this case, let's say we would conclude that she can tell the difference if her performance had less than 0.05 probability of occurring by chance. Then our rejection region would be 7 or 8. If she got 7 or 8 correct, we reject the null hypothesis. And that's because the probability of getting at least 7 is 0.035, and that's less than 0.05. On the other hand, the probability of getting at least 6 correct by guessing is 0.1445, and that's greater than 0.05. So if she got 6 right, we would fail to reject the null hypothesis. We never really accept the null hypothesis. We don't know for sure that she's lying, but we have no evidence that she isn't lying. When we carve out a rejection region, we're allowing ourselves the possibility of making an error and rejecting the null hypothesis even though it's true. This is called a type 1 error. In this case, if the woman is guessing, we have a 0.035 probability of concluding that she's not guessing. If the null hypothesis is true, we have a 0.035 probability of making a type 1 error. The type 1 error we allow ourselves is called the significance level. A p-value is the probability under the null hypothesis of observing a statistic at least as extreme as what you observed. If the woman identifies 7 cups, then the p-value is 0.035 because 8 is more extreme than 7, so we count that too. If she identifies 8, then the p-value is 0.004. If she identifies 6, the p-value is 0.1445. The rejection region is determined by the significance level. If the p-value is lower than the significance level, we reject the null hypothesis. The alternative hypothesis, HA, determines what is considered as extreme as what you saw. Notice that 0 and 1 are no more likely to occur than 7. I would have counted them in my p-value calculation if I were testing in both directions. But here, I'm only interested in whether her probability of success is greater than 1/2. I'm testing in one direction. If I were interested in whether the probability was different from 1/2, I'd test in both directions. and I'll get to directions in a minute. First, I want to warn you about a common misconception. The p-value is not the probability that the alternative hypothesis is true. It's the probability of taking a sample and getting a statistic as extreme as what you got if the null hypothesis is true. The null hypothesis specifies a value for a parameter. Under the frequentist interpretation of probability, the null hypothesis is either true or it's not. There's nothing random about it, so there's no probability associated with it. To a frequentist, it would be an abuse of the language to talk about the probability of a null hypothesis being true or false. And this is where frequentists and Bayesians fundamentally disagree on things. Because to a Bayesian, you can talk about probabilities concerning parameters.